So this is 13.8 part 2. So we said yesterday that that f, the extreme value theorem tells us that our function attains a maximum or minimum at a critical point. If we have a closed bounded region, so we have some boundary on our function, the extreme value theorem tells us that that we have a maximum or a minimum either at a critical point or somewhere on the boundary. So if we have a boundary on our function, then our critical points are going to occur either at our maximum or minimum are either going to occur at the critical points, which is what we talked about yesterday, or somewhere on the boundary. Just like we talked about with a single variable function, when you have a bounded interval and you want to find a maximum or minimum on that interval, you examine the critical points and you examine the endpoints. With a multivariable function, our endpoints, we don't have endpoints, we have boundaries, which are curves. So when we're examining the boundary, then we're looking for a maxima or a minima on this curve that's the boundary of our region. So we're going to start out by saying that our absolute maxima or minima, and I'm just going to say max or min, occur at critical points or on the boundary. Of some closed bounded region. So when we're looking for a relative extrema, we're going to go through several steps. So our first step is find the values of our function at the critical points. So that's what we did yesterday when we took our first partials and set them equal to 0, and then did our second partials test. So we're going to find the values of f at critical points. Our second step is going to be to find the extreme values of f on the boundaries. And then we just look at our list. We're going to have some list of values of f, and then we just choose. The largest is the absolute maximum, and the smallest is the absolute minimum. So the steps, the idea is not complicated. What makes some of these problems complicated is, one, the function can be complicated, so finding our critical points can get tricky. But then our boundary, depending on what our boundary is, we end up finding maximum and minimum values on these boundaries. And if the boundaries are complicated, then that problem in itself can get complicated. But the procedure is pretty simple. Do what we did yesterday to find our critical points. Then we look at the values of the function on the boundary and find the values there. Pick the biggest for the absolute maximum, the smallest for the absolute minimum. So questions on the idea? Okay, let's look at a couple of examples. So we're going to find the extreme value. So we'll just do two examples. We're going to find our extreme values of our function in the particular region. So for this one, we have f of xy equals 2x minus y squared. And our region R is the region in the xy plane between these points. Between 2, 0, 0, 1, and 1, 2. So if I were to draw a quick sketch here, I'll just draw the xy plane. So our region, we're going to have this triangle. So we have some function z that's up here above the xy plane, and we want the extreme values of z that are bounded by this curve in these boundaries in the xy plane. So that triangle is our boundary. So the first thing we're going to do is find our critical points on the interior of the region. So we're going to find our critical points, and we do that by what we did yesterday. We're going to set our first partials equal to 0, and since we're just finding the values of the function, we don't have to run the second partials test. We just plug our value in to f and see what it is, and then we're just going to compare our values. So our critical points are going to occur when our first partials each equal 0. So f sub x is going to be 4 times 2x minus y. And f sub y is going to be minus 2 times 2x minus y. So our first partials. And when we set each of these equal to 0, we want these equal to 0. When we set each one equal to 0 for each one, it gives us y equals 2x. So on the line y equals 2x is where these two first partials are equal to 0. So our critical points are along the line y equals 2x. So on the inside of the region, the critical points when y equals 2x, what I'm going to do is take y equals 2x, and I'm going to substitute it back into our function and find the value of the function along y equals 2x. So I'm just going to plug in y equals 2x, and what do I get? 0. So along the line y equals 2x, our function is 0. So that gives us one function value to compare. So we know that we have f equals 0 along the line y equals 2x. So now we need to examine our boundaries. We have 3 boundaries that we have to examine. We have to examine each of these segments separately. We have three segments that are the boundaries of our region, so we examine each one separately. So let's look at between 0, 1 and 2, 0 along this segment. Along that segment, I'm going to find an equation for the line that goes through that segment. Along that segment, we have y equals minus 1/2 x plus 1. and then I'm going to plug that y value into my function. So along that segment, we have f of xy equals, and when I plug minus 1/2 x plus 1 in here for y, I get that my function is 5/2 x minus 1 squared. And we want to maximize this function between 0, 1 and 2, 0. So where is it going to be on that interval? We could, if we wanted to, we could say, we could take the first derivative, set it equal to 0, and solve that way. This one's a little, we can look at it, be a little more, save ourselves a little work. So what's going to be the minimum value here on the interval 0, 0, 1 to 2, 0? Where's it going to take on its minimum value? Zero, right? So if this is 0, what I get, my value is 1. Anything else, anything between 0 and 2 is going to give me a larger value here. So this is going to be. What's that?
What about as it gets close to 2/5? Not at 2/5, but right before it's 2/5. That would give you close to 1 minus 1, which would be small.
2/5 is. What's 2/5 is a decimal?
There's no reason for x between 0 and 2.
Right, so x is only between 0 and 2. So we're only looking for the maximum minimum when x is between 0 and 2.
So wait, so what's wrong with 24?
Well, let's look. So let's take a look. Let's take a look. So when x is 2/5,
Well, no, it has to be slightly bigger or slightly smaller. So because if it's 2/5, it gives you 0. Oh wait, yeah, what's wrong with that? Yeah. Yeah, just 0.4. Oh shit.
So if x equals 0.4,
Yeah.
okay, if x equals 0.4, f comes out to be 1, right?
No, it's 0.
F equals 0. Okay. So then let's look at our other. So where are our other points going to be? We're going to look. We could look at our first derivative. We could take our first derivative, set it equal to 0, find the extreme values there, and we can look at our endpoints. So let's look at the endpoints of our interval here. So f of at 0, when x equals 0, f equals what? 1. When f equals, or when x equals 2, f equals 16. All right, so we have, so on that interval, my minimum is 0, and my maximum is 16. So those, we're going to take a look at those. We're going to keep a list of these and look and see where our maximum and minimum is. So now let's look at the next boundary between 0, 1 and 1, 2. On that boundary, we get y equals x plus 1. So we plug that into our function, and we get f is f equals x minus 1 squared. And we're going for x equals x between 0 and 1. So let's look at our endpoints. When x equals 0, f equals 1. And when x equals 1, f equals 0. Are there any points in between 0 and 1 for x that are going to give us something larger than 1 or smaller than 0? No. And again, we could take the first derivative of this, set it equal to 0 to get our critical points on that boundary. So now we have, so far our maximum here is f equals 16. And we have a minimum of f equals 0. And now we're going to look at our third boundary. So between 1, 2 and 2, 0. We can find the equation for the line there. We get y equals minus 2x plus 4. So f, when I plug that in for y, f comes out to be 4x minus 4 squared. And between 1 and 2, we're going to look at our boundaries on that region. So when x equals 1, f equals 0. And when x equals 2, f equals 16. So here's another f equals 0 value, and here's another f equals 16 value. And notice here when f equals 16, my point was 2, 0. And up here when I got f equals 16, I'm at the point 2, 0 also. So now we have all of our extreme values. Is there anything between 1 and 2, x equals 1 and 2, that's going to give us a value smaller than 0 or larger than 16 on that interval for that function? No. So our extreme values are absolute max. Absolute maximum is at 2, 0. And our function value is 16. And our absolute minimum is along y equals 2x. And the points where we found our function equal to 0 are each of those along the line y equals 2x. We found one at 1, 2, f equals 0. This one was at 1, 2, and this one was at 0.4, x equals 0.4, and we can figure out what y is there. So 0.4 and y is, if we plug in 0.4 for x here, what is it? 4/5. Is that along the line y equals 2x?
Yep.
Mm-hmm. So all of those where our function is 0 is along the line y equals 2x. So that's our function equals 0 along the line y equals 2x. So our absolute max would be 16, and our absolute minimum would be 0. The maximum occurs at 2, 0. The minimum occurs along the line y equals 2x. So let's take a look at what this function looks like on that region. So I have a graph of that. I should have brought it up earlier. I forgot. All right, so there's our surface and our triangle. That's our region. That's our boundary. So if we look get an angle here where we can look. So right along here, along this line, we end up with y equals 2x, where our function was 0, and then our absolute maximum was up here, where f equals 16 at the point 2, 0. So that's our surface on that, bounded by that triangle. So our minimum is along here, and our maximum is up here. So, not difficult work, but a lot of work. And if our boundary is more complicated, then examining the extreme values on the boundary can be a little more difficult. Questions before we go on to our next example? Okay. Let's look at one where our boundary is a little bit more complicated, but we only have two boundaries for this one. So our example here, f of xy equals 3x squared plus 2y squared minus 4y. And our region, we're bounded by the region R is region of the xy plane. Bounded by y equals x squared and y equals 4. So our region in the xy plane is going to be this parabola, like so. And we have this line up here. And these are going to intersect at 2, 4. It's where these two regions intersect, and negative 2, 4. Are these intersection points. So we're looking at that we want to find the extreme value of this function bounded by this parabola and the horizontal line. So let's find our critical points first. We're going to find the critical points on the interior. So what is our first partial derivative, f sub x? (6x). And the first partial f sub y with respect to y? 4y minus 4. So our critical points, where are our critical points on the interior going to be? X equals 0 and y equals 1. I wrote x, thank you. I'm thinking about what I write next, and then I get ahead of myself. And then so we're going to plug that point in to our function at 0, 1. F of 0, 1. Plug that in and we get negative 2. So at the critical point on the interior, our function value is negative 2. So there's one that we're going to compare. Now we're going to look at the boundary. Let's look at along y equals 4. Along y equals 4, our function gives us, if we plug in y equals 4 here, we get 3x squared minus 16. And x is going to vary between negative 2 and 2. Yes, you're right. 3x squared plus 16. And on this curve, along this curve, let's look at our endpoints. At plus or minus 2, if x equals plus or minus 2, our function value comes out to be, if I plug in plus or minus 2 here, I end up with the function value equals 28. where would be the minimum value here? X equals 0. So at x equals 0, my function value is 16. So along that boundary, we have these two function values to consider when we're looking for our maximum. Neither of them are below this. So far, this is our minimum. Along y equals x squared, or on y equals x squared. So we're looking at our second boundary is a parabola.
Why do you do x equals 0?
That would be the vertex of this parabola, right?
Okay.
We could do the first derivative, set it equal to 0, and come up with that. But I think what I did was I just looked at this and said this is just a parabola shifted upward, so that the vertex is going to be at x equals 0. So on y equals x squared, we're going to find our function value, our function. I'm going to plug x squared in for y. Our function turns out to be 2x to the 4th minus x squared. I just plugged in x squared for y into our function here and then simplified. And for this one, we can look at we'll do the first derivative test on the function along that boundary. So f prime here. F prime is 8x squared 8x to the 3rd minus 2x. And I'm going to factor that as 2x times 4x squared minus 1. So f prime equals 0 when x equals 0 and when x equals minus 1/8, or sorry, plus or minus 1/2. So doing the first derivative test on this boundary, I get that f prime equals 0 on the boundary when x equals 0 and x equals plus or minus 1/2. And then I'm just going to test those points to come up with a function value. So f of 0 we already know that when x equals 0, our function is actually on this boundary. When x equals 0, f is 0.
You're putting it back into, not putting it back into the first.
Right. So on this boundary, this is the function. The function is 2x to the 4th minus x squared. So when x equals 0, my function evaluates to 0. When x equals plus or minus 1/2, I'm just going to plug plus or minus 1/2 in here, and I get minus 1/8. So my maximum is at 28. When f is 28, that's my maximum. And my minimum is -2. So the absolute maximum on that region is f equals 28 at plus or minus 2 and y equals 4 there. And the absolute minimum is f equals -2 at 0, 1. And we take a look at a picture of this. So there's my there's my function, there's the parabola, turn it this way, the parabola, the line. So my minimum is at 0, 1. So right here, my minimum is -2. So it kind of dips down below 0 there. And then my two maximas are here and here. And if you have a more complicated boundary, then you have a little more work to do finding the extreme values on the boundary. Any questions? Okay. Homework. Just a few. So there you go.